Hey everybody, and welcome to NASA Science Live. I'm Molly McKinney, one of your co-hosts for today, as we join you from the Hampton Roads Convention Center right here in Hampton, Virginia, and cover day one of the 2021 Moon to Mars Ice and Prospecting Challenge brought to you by NASA. What's going on behind me? Why don't you all take a look? Students have gathered from 10 different universities across the country to test their original technologies to solve a lunar and Martian exploration dilemma, which is how to access subsurface ice and then melt that ice into water. Why is this important to NASA? Well, as we look forward to the Artemis program to the moon and even one day crewed missions to Mars, being able to access resources like water will be crucial for humans to survive on other worlds. So teams have been tasked with designing an ice and water harvesting system for use on both the moon or Mars. Not an easy task. And today they're testing their systems out in a head-to-head competition. Now we are in person this year. We've jumped through quite a few hurdles to make that happen. And we are following very strict COVID protocols to make that possible, including everyone on the floor wearing face masks. We are all fully vaccinated, or we've had proof of a negative COVID test in hand. Now, if you have any questions throughout the show today, you can send them in using the hashtag AskNASA, or you can leave a question in the comment box wherever you're watching from, and we'll try our best to get those answered for you today. It is a live show. That's one of the many perks of it being live. Well, I'm sure you can hear the excitement in this room. This is a real live show, so there's drills happening as we talk. But before we get into the competition, why don't you step over here, and I'm going to explain a little bit more of the process so you can understand how the Moon to Mars Ice and Prospecting Challenge works. So you'll see these blue bins at each one of the team stations. And situated at the very bottom of these bins is a block of water ice. Now the objective of this challenge is for teams to get their drilling apparatus or their drilling system all the way down to that water ice, and they're supposed to extract water from the ice. That's where these buckets come into play. You'll actually see water funneling into them. What's tricky about this challenge, if that's not hard enough, which that's hard, is hidden underneath is this word called regolith. You'll hear it getting tossed around quite a bit today, and it's actually simulated lunar or Martian terrain, because let's face it, on the moon and on Mars, we may not know what the soil is like underneath the surface. So teams have to be able to, as they're drilling down, collect data to put together a digital core. So if you think of a core sample when you pull it out of Earth, you see all these different layers of soil. So teams have to digitally gather how many layers they are, how thick the layers are, and how hard they are. Some layers may be really soft, some may be hard, more like a cement consistency. So it's a really difficult challenge for these teams, not to mention keeping in mind weight specifications and different dimensions that they have to focus on. So someone who can tell us a little bit more about why this technology is important into space is the special guest that my co-host, Natalie Joseph, has over at the correspondence desk. So Natalie, let's take it over to you.
Thanks, Molly. Hi, everyone. I'm Natalie Joseph, your co-host for today's Moon to Mars Ice and Prospecting Challenge, coming to you live from the Hampton Roads Convention Center. And let me tell you, you can just feel the excitement in the air as teams work diligently to extract water from these bins. I'm so excited because I'm joined by Alejandro Pensado, an aerospace engineer at NASA Langley Research Center. Thank you so much for joining us today, Alejandro.
Oh, thank you for having me.
Yes. So I understand that NASA is returning to the moon. Can you tell me more about this exciting endeavor?
Yes, of course. This is all part of the Artemis program. We're returning to the moon after 50 years of robotic exploration. This time with a sustained presence there. We're partnering up with industries in ways we haven't done before, and ultimately setting a precedent to keep expanding human exploration.
That is so exciting. So how does the Moon to Mars Ice and Prospecting Challenge help us achieve this goal of returning to the moon?
So we are going to the South Pole, somewhere where humans haven't been there before. And so, for example, one of the challenges is we don't really know what the surface and subsurface are made of. So one of the challenges that they're facing here is being able to demonstrate the capability of creating a digital core to identify the layers as they drill into them. And that's going to be a very useful capability that we'll need to use to explore the moon.
Mm-hmm. And why is NASA interested in harvesting water on the moon and Mars?
Being able to harvest water on on the moon and Mars it goes a long way for human exploration. There are multiple ways you can use it. It can support the day-to-day operations of humans in those locations, and you could use it to as fuel, propellant. So ultimately, having a sustainable presence in these locations, water is going to be essential.
And we keep mentioning water. So what do we know so far about water on the moon and on Mars?
So for both Moon and Mars, we've been studying what is there for quite some time now. For the Moon, there's been orbital missions that have identified water on the Moon, and more recently with an L-Cross impact mission, identified that there's water on the permanently shadowed regions of the Moon. Similarly for Mars, there's orbital missions that identified water, and since the Phoenix lander, we've been learning more and more about the water on Mars. Recent discoveries have shown that there might be large ice deposits beneath the surface, which makes this competition very important.
I bet. And tell me a little bit more about this thing called in situ resource utilization. What is it, and why is it so important?
So in situ resource utilization, or ISRU, is essentially looking at being able to use resources on site. So you can imagine that as we're going to be doing these more ambitious missions, we're going to be needing more and more of everything, propellant, consumables. And this is going to be more of a challenge in terms of if you have to bring everything from Earth. So then the question stems, can we use things that are on the Moon and Mars? And water being one of the crucial items that if you could use it, then you could be helping how things go in terms of the operations and potentially for refueling. So you can imagine you're lessening the challenges of having to take everything there. And similarly, maybe you can start making some design changes based off if you can use things that are already there. So ISRU ultimately gives us a lot of flexibility on how we can design these future missions.
Yeah, thank you. And something that I think, Alejandro, is super cool about this challenge is it's all about students and getting their ideas. So how can students, why is it important that we engage with them, and how might we use these students' ideas in the future?
So it's going to the Moon and Mars is going to be a challenge that we're not going to solve today or tomorrow. And in this long endeavor, it's important to engage with the students early on, because ultimately having them aware of what these challenges are, getting their ideas on these things will be critical, as they will be the ones that kind of answer these challenges down the line.
Yeah, and I've got a chance to kind of look around and I see all these really cool drilling systems, and people are already getting some water, and it's super exciting. Have you had a chance to walk around and take a look at the designs? Is there anything that stands out to you?
Yeah, it's very exciting to see the designs in action. It's very interesting to see how they've been refining and working off of ideas from previous years. You can see that they all have their kind of unique design choices on how they did like the structural systems and so forth. And then they're still doing some interesting trade studies where how do you extract the water in terms of a liquid form or a vapor. So they're getting a chance to test all these ideas, and I'm excited to see how they come out.
Well, thank you, Alejandro. We actually have some questions coming in from our hashtag AskNASA, and you can submit your questions. Just use that hashtag AskNASA. So, Alejandro, Emily on YouTube asks, are there any future plans to launch to Mars from the Moon, since the Moon's gravity, well, is much smaller than the Earth's?
So that is part of a trade study that is being conducted. Obviously, there are benefits into using a lower gravity well as a launching point, but there's so many pieces along that way that we're still trying to figure out the benefits and how we can go about that.
And Brittany on Twitter asked this question. I love this question, Brittany. Is it really safe to drink Martian or lunar water?
So the answer is carefully. This is going to require pushing the technology to make sure that we can process it. There will need to be a filtration system. So I will go with a maybe.
Maybe. Okay. We'll see. So we have one more, our final Ask NASA question for you, Alejandro. And Scott on YouTube wants to know more about the new Viper mission that will scout for water on the moon. And actually, Scott, we just selected the landing site for the Viper rover on Monday. So that's a great question. I love this. So Alejandro, can you tell me more about that and how the Viper rover ties into this competition today?
Of course. So yes, the landing site was recently selected. It was selected for the Nobile region near the South Pole. So one of the challenges is we know there is water there, but we don't know exactly in what concentration and distribution is there. So Viper is going to answer those very questions and give us a better idea of kind of a resource mapping. And based off that, it'll give us a better idea of how we can extract the water from those areas, which is in turn going to guide us in how we can develop these ICU technologies that you see today.
Great. That's so exciting. I am really, really excited about all of these missions we have going on at NASA. So Alejandro, thank you so much for joining us today.
Of course. Thank you for having me.
Now, Molly has some exciting things to show you all out in the pit. But first, let's learn a little bit more about NASA's upcoming Viper rover.
We know from decades of study that the moon has water, but where and how much? In 2023, a robotic rover will explore the moon's surface in search of water ice. NASA's Viper moon rover will perform the first resource mapping mission on another world, using advanced instruments and tools to determine the location and concentration of water on the moon.
To send Viper to the moon, we're leveraging industry as part of our commercial lunar payload services program, a program designed to send science instruments and technology payloads to the surface of the moon. Viper represents a very different development paradigm. We are developing each instrument for launch on Eclipse ahead of Viper, totally flipping on its head how we normally do this. This is truly creative. An industry partner will launch Viper to the moon's south pole. This is a place where no human or rover has ever been before.
The rover's survey will provide scientists with the most detailed view of the moon's water to date and point to spots where water could be harvested by future astronauts.
Viper will be the first resource mapping mission on the surface of another celestial body. It represents a new kind of mission for NASA in which the objectives of advancing science and human exploration are closer than ever. The measurements that Viper's instruments will make can help us understand the source and distribution of the water and other volatiles on the moon, giving us insight into the evolution of the moon and the Earth-Moon system. The moon's water is also a precious resource that could be extracted to support human exploration of the moon and beyond. What we learn from Viper will bring us a step closer to developing a sustainable, long-term human presence on the moon.
Go Team Viper. We are proud of you all. Looking forward to it. For those of you just joining us, we are coming to you live for NASA's coverage of the 2021 Moon to Mars Ice and Prospecting Challenge. Now, as you look around the pit area today, you'll notice that each of these teams have a different design that's really unique to that team and to that university. Each team brings a different idea to the table, and that diversity of ideas that we get from, including students in a competition like this, really helps us expand our collective understanding, not just for NASA, but really as a global science community. Now, this is the 5th year of this competition, and every year we really learn something new. What worked, what didn't work, and this collective knowledge from student-led ideas can really pave the way for future crewed missions to places like Mars and the Moon. Today is day 1 of this year's competition, and teams are operating their systems for the first time. I was talking to a couple of the teams yesterday, and these systems had never traveled before. So it's always a little nerve-wracking powering these on for the first time. Most of the university students today are using a drill to dig through the simulated lunar and Martian soil to get to the ice below it. And along the way to the ice, teams have to collect data about the layers they're drilling through, how many layers there are, how thick they are, how dense they are, and they'll use this information to create a digital core that they'll be judged on at the end of the competition. And then to extract the water below, teams have converged upon a strategy of melting a pool of ice underneath the surface and pumping it out. rather than trying to extract the ice from the overburden layers up above. Yep, okay. So now that you all understand a little bit about the competition, let's go talk to some of the teams out here on the floor. Our first one up here is from Stevens Institute of Technology, and you made it easy for me. I don't even need the cue card for this one. Steven, yep. Nice to meet you.
Nice to meet you.
So tell me a little bit about your design and if you modeled it after anything.
Sure, so that is the Extractinator. Very much like a 3D printer, we're able to translate our drill and extractor back and forth, forward and back, and up and down using stepper motors. Our drill is a commercial off-the-shelf rotary percussion drill, which has a 1/2 meter long drill bit. While we're drilling through the overburden layers, we use system telemetry to map out our digital core. So we're measuring things such as weight on bit, feed speed, RPM, current, voltage, all of that. And that goes into our MSE calculations, and we can calculate the hardness of each of the layers. After we're done creating our digital core, we retract the drill, move the extractor over, and lower it down into the hole. We use a 750 watt cartridge heater and a peristaltic pump.
That should do it.
Yeah, it's pretty strong. We create a rod well, so while we're also extracting the water, we're also simultaneously circulating the water to further melt the ice. And then once we collect the water, it goes through our sand filter and then into our collection container.
It sounds like you thought this through.
Just a little bit.
Now, your team has competed before. What were some of the challenges you ran into in years past, and how have you compensated for some of those this year as you compete?
Sure. So 2 years ago, our team faced the issue of over melting the hole. So as they were melting the ice, water was leaking out the side of it and down the test container, making it unretrievable. So to fix that issue, we installed an optical sensor. So that tracks the water level of the ice, of the water as we melt it. And combining that with our rate of penetration into the ice and the time that the pump is running, we're able to estimate a radius of the hole that we melt, so we can also map out the ice as well as the overburden.
Having addressed that, how do you feel about your odds this year of winning?
We feel pretty good. We have a few more issues to work out, but once we get going, I think we'll go strong.
Cool. Well, we'll be rooting for you. Thanks so much for your time. I'll let you get back to it.
Thank you. It's been a pleasure.
Yeah. Let's go over here. We've got one more team to interview. Arturo over here from AMD, correct?
Yes, ma'am.
So Arturo, tell me a little bit about your design and how long you've been working on it.
So this project, we've been working over a year, and it has 3 subsystems. So the main attraction is our tensegrity structure. So it consists of aluminum rods and high molecular weight polyethylene cables. So it's 1/8 of the weight of a steel cable and 50 times the strength when compared to a steel cable in tension. So when you're doing a space system, you really want to do lightweight. So that was our first idea, and we went with that. So following
light and tight.
Yes, ma'am, that's right. And then following that, we have our 3-in-1 system. So it's able to drill, extract, and heat the ice to melt it. So that system was integrated all throughout, and it was a great opportunity to do all things without moving the drill. And just even to go down once and then just stay down there and do the whole process as well. And then lastly, you have our mounting structure. It's an aluminum railing system, low friction carts that's able to move the rail around in case we need to make another hole as well. Yes, ma'am.
And of course, you did all of this in the midst of a global pandemic, like all the other teams here. How did COVID pose some challenges for your team?
Of course. So the main thing was communication and manufacturing. So communicating with our team was, slower. Everyone's at home. The machine shop was closed. So the way we overcame this, we pulled together, knowing that if you didn't do your stuff at home, you couldn't meet at the lab or someone else could do your job. So everyone came together and kind of did their part, knowing that we were counting on them to do their stuff at home. And, the manufacturing machine shop was closed, so we ran into a lot of issues there. But, adapt and overcome and, make sure we tackle the task ahead for sure.
How do you think your team did enduring all of those hurdles they had to hop through to still make it here and be here this year?
Of course. I mean, we did a great job, in my opinion. We have a diverse group of engineers. We have mechanical engineers, petroleum engineers, aerospace engineers. So everyone having different disciplines and different backgrounds that gave us the edge of cover all our bases and have different viewpoints and successfully present a project here at NASA.
Well, we're really excited to have you guys here. Thanks for taking the time. Good luck. I think you'll hear that common thread throughout this competition that COVID-19 pandemic really posed some hurdles. This is a difficult challenge to begin with, and then to add in, manufacturers being closed and restricted access to different facilities, a lot of the resources they had planned on using for these. One of the teams back here is using wood instead of aluminum. They weren't planning to send something to space made of wood. So we have a video to take a look at really quick to give you a little more background on that.
The 2020 virtual Moon to Mars Ice and Prospecting Challenge tasked university teams with coming up with novel solutions to extract water ice beneath the surface on the Moon and Mars. These are some of the novel ways that last year's teams came up with to solve this unique challenge.
Our drill idea, the unique thing about it was pulverizing the overburden and then sheathing the hole, augering out the dirt.
Melt the ice within the simulated test bed, and then we would recirculate it back down, which then heats up more ice around it.
We have a second tool that rotates and articulates out, melt downwards, and then melt out.
We borrow from the aerospace. It's a kind of structure called tensegrity structure. It's a kind of rods and string. It is not like our house structure.
What we were trying to do with Leslie is incorporate laser heating into our system for the extraction of water.
With the onset of the COVID-19 pandemic, universities across the country restricted access to on-site facilities, greatly impacting the Moon to Mars Ice and Prospecting Challenge student teams.
We had constructed all of our subsystems. We were in the middle of putting them together when everything hit.
As spring break happened, then everything with COVID started to ramp up.
By a week later, MIT had already sent all undergraduates home. It was very sudden, yeah.
We thought that we would just be able to do some design work and stuff from home for a couple weeks, then go back and get access to our lab again. But it became evident that that wasn't going to happen.
So we rushed over, collected all of our supplies, threw them in the back of one of our teammates' trucks.
And so we had to take all the parts that were originally designed to be machined in our machine shop and then redesign them for 3D printing and other things you can make at home.
We were actually a few hours before they locked the doors for 3 months.
I don't want to sugarcoat anything. Obviously, we lost the full head of steam that we had. We hit that brick wall of COVID-19.
When things moved online and everyone had to go home, a lot of people kind of gave up.
A lot of the team members did step back and kind of focus on their own things, but still we were trying to get a great paper out.
So the only thing I can do at this time was to keep a Zoom meeting between every team member.
We used Discord and Zoom.
For each one of those meetings, we had a Zoom call.
We Zoom calls.
We stayed together using Zooms.
Try to do this over Zoom or Microsoft Teams.
It was just like a snap of the finger and everybody just got right back on board and was able to let's finish this, let's do this, let's prove ourselves right.
Because we knew at the end goal we could still present something, and the chance of that kind of pushed us.
Going into a second year with a head start and also a lot more wisdom would be really helpful.
Our senior project's actually done. We finished up all of our testing, we made that push, and we're handing it off to the next senior project team that should carry it on for the next 3 quarters.
Luckily, all of us were freshmen, so we have many more years that we'll be able to refine our design and then go back.
We expect that the people who were working on last year's design to keep finishing and tweaking last year's design as much as possible and getting the best results on that one. And then the new 27 members that we just brought in will work on a completely new design from scratch.
It's an entirely new team this year. They have some very good ideas about things that we hadn't even had time to consider.
We are already planning to do everything that we were going to do this year. We will do it next year.
We're definitely very appreciative of the opportunity to get to work and learn through this whole process. So we'd like to thank NASA for sure.
If you are just now joining us, we're coming to you live from NASA's Moon to Mars Ice and Prospecting Challenge, where teams are drilling through simulated lunar and Martian regolith or soil to get to the ice in hopes of extracting water from down below. And I believe my colleague over there, Natalie, has one of the event organizers. So let's kick things off over to Natalie at the correspondence desk and hear how this competition came to be. Natalie?
Thanks, Molly. And yes, I am here with someone very important. I'm joined by Shelley Spears, who's in charge of bringing this whole event together. Thank you so much for joining us, Shelley.
Thank you, Natalie. It's wonderful to be with you.
Yes, thank you. Yeah. And we're back for another competition. So how is this year's competition going?
It's going fantastic. These teams really came ready to compete this year. As you can tell, or just hearing all the drilling and all the excitement in the room, we are off to a fantastic start.
That's so great to hear. And I know, especially because I understand that last year's competition was canceled due to the pandemic. And so I know for you, it must be just so great to see all of these designs here in person and seeing everything in action today.
Absolutely. They worked so hard on this throughout the year, and they've had so many challenges putting their systems together with all of the hiccups and obstacles of COVID. And so to have them actually physically be here to put all of their hard work to the test and compete with their colleagues at other universities, they're excited, we're excited. And it's really great to see people face to face again.
I agree. So Shelley, this is the 5th year of the Moon to Mars Ice and Prospecting Challenge with new teams competing with new designs. What have we learned so far over the lifetime of this competition, and why does NASA continue to support it?
So we've learned when we first started the competition, there were so many different approaches to solving this complex challenge. And over time, we've seen teams start to gravitate towards one or two approaches as they learn through reading technical papers and lessons learned and all the knowledge capture that we do, because it's a competition, but we're all in this together. So we want to share all the best practices, everything that works, everything that doesn't work. So maybe even more importantly, we've learned what doesn't work. And now we're starting to gravitate towards a couple of approaches that are working well, but we don't want to make it that easy on them. So we keep adding complexity to the competition, things that will help NASA, such as the drilling telemetry and some other elements to keep it really hard for them.
Yeah. And why do you think competitions like the Moon to Mars Ice and Prospecting Challenge are beneficial?
Well, they're important for a lot of reasons. For students that are entering the workforce and want to go into aerospace and exploration systems, it gives them the opportunity to apply their skills in a very hands-on way. It helps. It's a very cost-effective way for NASA to be able to put out these complex challenges to academia, because let's face it, it's going to take a lot of innovative and creative inputs to solve some of these complex problems. And so it takes industry, it takes academia, it takes our partners in international space agencies, all of us working together. It also creates a very rich talent pool for industry and for NASA. And let's face it, these students here, when we go and have longer duration human presence on Mars and Moon, it's going to happen during their career. So they're really getting a good head start.
And how can students get involved in future challenges?
There's so many opportunities out there. So whether you're in kindergarten or even some preschool all the way through graduate school, NASA does a great job of trying to create opportunities for students. So I would say to go to NASA Express. You could just search that in the internet, and NASA Express is a newsletter, and they do a wonderful job of letting everyone know all the opportunities that are out there.
And Shelley, how about just getting involved specifically in the Moon to Mars Ice and Prospecting Challenge?
So you can go to the NIA website or to the NASA website and just do a search. Do NASA Moon to Mars Ice and Prospecting Challenge, or go to rascal.nia.net, and you can find the competition and you can see all about what we're coming up with next.
Sounds good. Well, we have so many Ask NASA questions coming in from our live viewers today. And if you're at home and you'd like to have your question answered live on today's show, use the hashtag AskNASA and drop your questions in the comment or the chat box from wherever you're watching us today. So Shelley, our first Ask NASA question comes from @IMainHuman1 on Twitter, and they're asking, what are the colleges that are participating in the challenge?
Okay, let's see. I could start around the room. Okay.
There's 10.
There's 10. There's 10. So there's MIT, Virginia Tech. Is it okay if I do this? Okay, I don't want to leave anybody out. Okay, Auburn University, MIT, San Diego State, Stevens Institute of Technology, University of Pittsburgh, Cal Poly, Northeastern South Dakota State University, Texas A&M, and Virginia Tech.
Great. Awesome. Well, congratulations to all those universities for making it out here today and getting this far. So we have another question from Kala Subtle on Facebook, and she wants to know, how were these teams chosen?
Okay, so we put out a call for proposals across the country. It's open to all U.S.-based universities. They can partner with international universities if they'd like. And we put out the specs and requirements. They submit a project proposal plan. It's reviewed by industry experts and NASA experts, our judging panel. We pick the teams that seem like they have innovative ideas and also seem well prepared to compete. And then we do a down select. We give them some initial small amount of funding to start with their software and hardware designs. And then they go through another mid-project review, and then they make the final cut, and now they're here.
All right. Well, thank you so much, Shelley. Thank you for joining us.
Thank you, Natalie.
Yes. And Molly, it's back to you.
Thanks, Natalie. And thank you, Shelley, for putting on another great competition. We love coming to this one. Well, I also had a really neat opportunity to interview Crew 1 NASA astronaut Victor Glover. If you've never heard him speak before, get ready, because he's an amazingly well-spoken person, and he's just a genuinely wonderful human being. And we get to talk about this challenge and what it means for astronauts like him who might actually be an end user of this technology one day. So, and he does know a thing or two about space firsthand. So let's take a look.
Victor, thank you so much for joining us today. We are so excited to have you on the show.
Molly, it's great to be here. Thank you very much.
So right now in the competition, our student teams are operating their unique technology, and they're demonstrating drilling through our simulated lunar and Martian surface, and they're trying to access the water ice that's hidden beneath. I'm curious, for you as an end user that might benefit from technology like this, what value do you see in competitions like this?
You know, first of all, I have to really just appreciate that statement, you know, as a potential end user of this technology, that it's amazing that we're going back to the moon with Artemis and the goals of the Artemis program. And so it's actually amazing that our generation is going to have a moon mission, a moon program that's going to send us back. And I'm really excited about that effort. And so for these students to be working on technology for us to get access to ice, which is a valuable resource, you know, because you need it for life, but you also need it for propulsion. It's a great component in rocket fuel. And so this technology is going to enable us to find new ways and new ideas for extracting this valuable resource from these sources that we've actually recently discovered on the moon.
I'd like to focus a little bit on the water component of that, because for you, when you've been in space, water is such a limited resource. I imagine you have to treat it with a lot of care. What does water signify for you? I assume it's different than what it signifies for me here on Earth.
Well, you know, it's interesting. Living in space helps you to appreciate the things that we take for granted, or at least really just expect to be there, like water. You know, in space, we have to reclaim water. We actually take, you know, I heard someone say once, I believe it was Mike Fossum, we turn yesterday's coffee into tomorrow's coffee. It's because we take the water out of everything. If I run on the treadmill and sweat and wipe my face with a towel, I hang that towel up, and the air conditioning system will dry it out and pull that moisture out of the air. And our air conditioner will separate it, take the moisture out, put it in our water system that purifies it and turns it into drinking water. Water is extremely valuable, and so it represents life to me. I think that's the most exciting part. The ability to get access to that resource that is already up there on the moon is a critical capability, a very, very neat thing to be able to do. And this technology that these students are working on, the ingenuity, the new ideas, I mean, they're not all going to take the same approach, and that's one of the things I think is really exciting about this type of competition.
How do you think, as an astronaut, technology that's derived from competitions like this one, the Moon to Mars Ice and Prospecting Challenge, could directly impact you and other future astronauts as you explore the moon, as you explore Mars?
You know, knowing that these students are creating something that might be a tool that we use in space one day is actually quite motivating and inspiring. And to see some of the ideas they come up with, but more importantly, I think the ideas they come up with are great. But then to see the physical competition where they show their hardware, they have a design, some of it they've had to code for, and they put all of that together, hardware and software, and they put it out there, and then they run it. They have to come up with procedures, they have to communicate, work together as a team, and move this material from one place to another. It's so amazing to actually see that idea become a reality. And so this type of competition, I think, is so important to inspire those students to dream and create, but also for us to learn about what ideas are out there, because NASA has some very good things that we've done for a long time that are working and they work well, but that might not be the best or most efficient way to do things right now.
Victor, thank you so much for your time today. We are so appreciative.
Thank you, Molly. It's been great talking to you, and congratulations to all the students and advisors at the event. Best of luck to you.
If you're like me and could listen to Victor Glover talk all day, stay tuned for part 2 of our interview where we talk about NASA's Artemis mission, and we get to hear from him firsthand what it would be like to actually be using this technology on the moon one day. So stay with us. You don't want to miss that. And if you're just now joining us, we are coming to you live from the Moon to Mars Ice and Prospecting Challenge, where university teams are drilling through simulated lunar and Martian soil in an attempt to extract water from the ice below. Now, one day, systems like these could be used to extract water ice below the surface of the moon or Mars. And for future explorers, being able to access resources like water will be crucial for creating a sustained human presence beyond Earth. So now that you get a little bit of context about the challenge itself, I'm joined here on the floor with some of the team so we can see how it's going in the pit area. So Pollock and Eric, you guys are both from MIT. Pollock, give me just a rundown of your design and your system.
Right, so I just first of all like to say that we've got an amazing team of 7 people, and we have complementary skills, and it's just amazing what we've actually come up with. So we have a really stable rig this time, and we focused on that a lot. So we've got a parallel drill and a heater as well. So first we drill a hole that's about 1 inch in diameter, and then we use a servo motor that's really accurate. And on the y-axis, we move the heater into place right above the drilled hole. And then we drop the heater down and use radiative heating to melt the ice, and basically going into Mars, melting the ice, and we use a pump to pump the water out. And so, yeah, that's basically the hardware of what we do, and this can be controlled by a team of, I guess, astronauts, where we don't actually have to touch the instrument, and we're just working on the, just controlling it from a distance. And I've been really lucky, and I've gotten to actually be one of those astronauts for our system. So yeah, that's exactly how our hardware works.
So it's not autonomous yet. It could be, but right now it's hands-off. And while it's hands-off, the software side takes over, which is your department, Eric. So walk me through some of the software and some of the unique tools that you're using to get some of your data, especially for that digital core.
Right.
I heard it's something like this.
Okay, cool. Yeah, so, first off, we got a microphone. We got it closely attached to the drill. And, getting water is nice, and we've done a fantastic job at doing that. But one of the main things that, we really want for the moon and Mars is to understand what are the layers that make up the thing we're digging. So one of the many things that we have is a microphone, and, you can sense the vibration, the different kind of sounds whenever you're drilling into a different kind of material. The other thing is a weight on a bit sensor, so whenever, more force is being applied to the drill, we would know immediately. More current is being applied to it, more current to the, the drill, the motor, moving the drill downwards, and you can also read the current of the drill bit, as well as, yeah, that's pretty much it. And we have all of that, and then we map it into like a neural net. So a combination of data, heavy statistics, and then you can figure out, okay, I'm drilling in clay right now, I'm drilling in concrete right now, I'm drilling in soil right now, I'm drilling in ice, and that's how you want to turn on the heater, you want to put the heater down, melt the water, and get water up.
I've covered this competition for years, and I hadn't seen a microphone before. I wouldn't have thought to utilize a wave file like that.
Yeah, it's it was just at the very end we were realizing, oh, it's making different kind of sounds. We can probably figure out what sounds it is, and there we go.
How confident are you in your ability to capture a clean water sample from this? Would you drink the water that your system produces over here?
Yeah, I would drink the water. It's relatively clean. I've drank dirtier water in my life before. But,
all in the name of science, right?
Yeah. And obnoxious, dealings with.
We'll take it. It's a live show. Well, thank you guys so much. I know you have a bunch of work to get back to, so thank you very much. I appreciate your time.
Thank you so much for having us.
Yeah,
thank you so much.
Let's come over here. We've got someone else to talk to really quick. So this is Cole. Cole, you're with the University of Pittsburgh, right? So Cole, tell me a little bit about your machine, your design.
Sure. So our system is actually pretty unique when you compare it to the rest of the systems around here. We're the only team this year to attempt to extract water as a vapor instead of a liquid.
Then he asked the question, are we doing the right thing? If no one else here is choosing that approach, why did you choose that approach?
Well, we really fell in love with the theme of this competition, which is to build a robot that could extract water on Mars and on the moon. And the conditions on Mars and on the moon suggest that you can actually have ice sublimate directly to a gaseous form when you add heat. And so...
Easier than here on Earth?
Yes. So we're actually having the hardest time competing here on Earth. And if we were to send our system to the moon, we'd actually have an easier time.
We'll have to talk to Shelley, one of the event organizers, about maybe just doing it up there next time. Be easier for you guys.
Yeah, I think the CTO of NASA told us we're going to ship it up there next week.
Wait, seriously? No. Oh. I was like, no one told me. It's not on my cue cards here. Well, have you burned through any heating apparatus today to get to this point?
Yes, we've already gone through one heating element. But I have great news. A couple hours ago, we actually were able to extract some water.
I didn't know that.
Yeah,
oh,
thanks.
Man, it's
all right.
But yeah, nice.
That was good.
That's great. Congratulations.
Yeah, I was super excited. It's amazing. And special thanks to my whole team. We all put in a ton of hard work this past year, more than I think we all expected. But we rose to the challenge, and I'm just super proud of all the guys that we have with us today.
Oh, that's awesome. Congratulations, Cole. I'm really excited for you guys. We all are here. This is not an easy challenge, and one of the things that, you can go ahead and get back to it. One of the things that I think is really important is the judges here. So Natalie over the correspondence desk has a special guest that knows the in and outs. I might even argue the official in and outs of this challenge. So Natalie, we'll kick it over to you at the correspondence desk.
Yes, Molly, I do have a very important person with me. I'm joined by Chris Jones, and he's one of the judges of today's competition. So happy you could join us, Chris.
Natalie, it's great to be here.
Yes. So, Chris, you've been so instrumental in the creation of this challenge. So you're probably the best person to ask. How does this challenge work, and what do students need to accomplish?
So we really have two big challenges that we're asking the students to do here, and it's why we call it the Moon to Mars Ice and Prospecting Challenge. Part of that is the prospecting side of it, and what we're looking for here is for teams to be able to give us what we call a digital core. We've given them these test beds that have multiple layers, but they don't know what those layers are before they get to the ice. So we're asking them to use the sensors and the instruments they have aboard their systems to determine what those layers are, how hard they are, how many of them are there, and give us that information back as a demonstration of the kind of thing we could do as we're exploring Moon in Artemis.
Mm-hmm. And then they need to, once they find that core, they need to find and collect water also. How does that work?
Right. So the other half of this is getting to that ice that's at the bottom of the cooler and processing that in some fashion into water they can deliver to us. So they know there's ice there. They've designed their systems to acquire it, but they also have to design these systems such that they have forward application to future missions we would do on the Moon and on Mars in order to be something we can use someday in a real mission.
Mm-hmm. And then after all of that, Chris, how does a team win the Moon to Mars Ice and Prospecting Challenge?
Okay, a big part of it is how much water can you deliver to us? You get a lot of points for showing up with a lot of water that you produced. But beyond that, the quality of that digital core. Did you understand the layers you went through? We give you points for that. The teams have also written technical papers that explain not just how their concept works here for the Earth demonstration, but also how it would be adjusted to work on the Moon and on Mars. What's the path to flight so that we at NASA could potentially take advantage of this? And all of the points for that come together to determine who's going to be the winning team.
Mm-hmm. And speaking of taking advantage of it, what's on the line here and what can students win?
So among the things that are on the line here is the glory of doing this. But more realistically, and maybe of more interest to the students here, we have a $10,000 prize pool that the judges will determine how to distribute among the teams. In past years, we've used that as a travel stipend to attend the Space Resources Roundtable, but it could also be used for any number of other opportunities for the students to go and present their ideas to a broader audience. And in addition, they get the opportunity to provide these really cool ideas to us here at NASA for us to hopefully someday build and fly.
Very cool. So we've got some questions coming in from the hashtag #AskNASA for you, Chris. So our first question is from a YouTube user, and they're asking, what are a few things that might differ in experimenting on the Moon and Mars?
Okay, the two definitely are different environments, Both of them are much lower gravity than we have here on Earth, so teams would have to understand how to deal with that. On the moon, there's a vacuum, which means that there is no air surrounding them at all, and that's going to significantly impact the ability of a system to use certain kinds of pressure in order to acquire the resources. In both locations, they have to deal with dust, but the way the dust behaves differs on the moon and on Mars. In addition, the ways in which we might find ice are going to vary between those two. On the moon, we're probably going to find that in a permanently shadowed region, which means we have to operate in cold and in darkness. On Mars, we're hoping we can find it in much more accessible locations.
Mm-hmm. And so Savant De Silva on Twitter, on YouTube asks, what's the sole purpose of extracting water from the moon?
Ooh, on the moon. So I think one of the biggest reasons to extract water on the moon is it's a chance to make up not just the life support goods that astronauts would need, things like water or breathable oxygen, but it's also a way to get the propellant they would use in the course of doing missions, leaving the lunar surface and going back to Earth orbit. One of the things I've actually looked at and worked with a number of folks on is when and where is the best location to use lunar ISRU? Where is it best to use that lunar water to support exploration? And the answer is there's a lot of possibilities there for how it can really benefit us.
Okay, cool. So we have another question from Twitter this time. And Amber wants to know, due to the freezing temperatures on Mars, how will you keep the water from refreezing after it's been extracted?
It's an interesting challenge, and it's not the only challenge we have with managing the water. Because of the low pressure there, water is also at risk of turning directly from ice into a gas, which means that we can't even capture it as a liquid. Some of the teams here are looking at using and taking advantage of that, but often it's a balance of keeping it warm enough, keeping it pressurized enough with additional systems in order to make sure that we can keep it in a usable state for future missions.
Cool. And Chris Fair on Facebook asks, if you do find launching from the moon to Mars as a viable option, what would you first have to transport to the moon to ready a launch?
Okay, so in order to take advantage of this, we're going to need the systems that can find this ice before we can ever take advantage of it. Then the systems that can mine it, process it, store it, turn it into something useful. And it's going and demonstrating all of these and doing the science that's needed to find where it is in order to turn it into something we can do.
Very cool. Kind of like the stuff we're doing today.
Absolutely. This is a great first step.
Yes. Well, thank you, Chris. It has been a pleasure. And I know you not only put this competition together, but you're also a judge. So I'll let you get back to that.
All right. Thanks, Natalie.
All right. Now, Molly, back to you.
Thanks, Natalie. As some of you all might have seen earlier in the show, I had the amazing opportunity to sit down with astronaut Victor Glover and talk about this challenge and how it affects astronauts like him that might be end users of this technology today and might also get the opportunity to walk here. So let's take a little look at what Victor had to say.
As we speak, NASA is actively preparing to send humans to the moon as part of the Artemis program. So what is Artemis, and is it essentially the next Apollo?
You know, I think that's an easy way to describe it, but it's not the next Apollo. It's our generation's moon program. It is Artemis. But if you're familiar with Apollo, it is a similar concept. We are building a very large rocket, SLS, which stands for the Space Launch System. It's going to be a very powerful, very big rocket that's capable of getting a spacecraft, Orion, to lunar orbit, which will enable us to get humans there and to a gateway, which would be like a space station that's orbiting around the moon. We'd be able to get humans to the gateway or to a human lander system that then could get human beings to the surface of the moon. And then one other very exciting component is Artemis astronauts. And so we're starting to identify folks that are going to be a part of it, and we call it Team Artemis. And so we're going to start, hopefully in the very near future, actually naming folks from Team Artemis, but also the Greater Astronaut Office, as well as our international partners to these missions specifically, and those will be the actual Artemis lunar astronauts. That's very exciting, very exciting.
How would it feel to be the next person to walk on the moon? What would that mean to you?
You know, I have no idea. I mean, I thought going into space and living on the space station was going to feel a certain way, and it did, but also so much more than that. It blew away my expectations. And so I could only imagine not even going to the surface of the moon, but actually being in orbit around the moon, before you go down to the surface, orbiting the moon and being able to just look out the window and see Earth rise. I mean, think about that. That picture that Bill Anders took, changed the way people saw themselves and when they see our planet. And so for me to be able to witness that with my own eyes, or even to be in mission control as the communicator, as the Capcom, speaking to crew members, my colleagues, my friends, while they're experiencing that, it would be unreal. And so I really couldn't tell you how it would feel, but I would love to go and have that experience and then come back and describe it to you.
One of the things I love about being a part of competitions like this is you see people come together as the human race, and you see all these different walks of life, people from different backgrounds. They speak different languages in many cases, and you really get to see this beautiful picture of our world and of our planet. Does having a view of our planet like that you've been able to have, has it changed your perspective on what life is like here?
Going to space, one of the things that it makes you do, I believe it would do this for all people, is it makes you appreciate life right there on the surface. You don't get to you see the entire oceans, you see these countries without borders, you see entire continents. It's amazing, that perspective. Doing any of these amazing science and technology things, like living in space, putting humans in space, requires us to do our best in just about every science and technology endeavor that we've had. Life support, medical, health, radiation protection, water reclamation, waste management, and all of those things drive us to be our best selves, and they remind us that we need the best from everyone. And that's what's great about these competitions, seeing these students from all over the country, from all these universities, especially my alma mater, Cal Poly. Go Mustangs, learn by doing. It's great to see all the walks of life, all the ideas and the ingenuity that comes with all of us doing our best together.
Well, Victor, thank you so much for your time. We are so appreciative of having you on the show.
Molly, thank you for the time. It was great to be here, great talking with you, and good luck to all the students and advisors in the competition.
Astronaut Victor Glover, folks, pushing us to bring out the very best in all of us.
Yes, that was so inspiring. Actually, I think I got goosebumps during it, Molly. And
I wasn't going to say anything because I was in that segment, but he's just amazing.
Yeah, it was awesome. I can't wait to see the rest of it. And I'm sure other people are wondering, too, how they can watch the full interview. And you can see that on YouTube/Science@NASA. So go check it out.
Do I have to deliver the bad news?
I think you do.
Yep. I just got comfortable over here. Unfortunately, we're out of time. But I tell you what, we have seen some really amazing prototypes today. I've seen designs I've never seen here before covering this competition. So I truly believe we've heard it over and over again today, that the technology that's being developed today will really help us advance exploration as a whole in space as we start to pursue other worlds like Mars and, of course, the moon.
Yes, and it's really going to be these students' ideas and the ideas of the future that are going to help us take that next giant leap. And I'm very excited.
Me too.
And I want more people to get involved, and I think people are wondering how they can do that. So if you want to get involved and you're curious about more challenges like this, you can subscribe to the NASA Express newsletter at nasa.gov/STEM/Express. And if you want to learn more about our very exciting Artemis program, visit nasa.gov/Artemis. All right, well, thank you for joining us today on NASA Science Live. I'm Natalie Joseph.
And I'm Molly McKinney, and we'll see you next time. Thank you.
Bye, everybody.